Alrighty. So the first thing that we're going to talk about today is we're going to develop some frequency domain relationships for circuit elements. And this is leading us towards impedance. So let's start with a simple resistor R, across which there is a voltage V of t and through which there is a current I of t. And let's say explicitly that the voltage drop across our resistor is a sinusoidal voltage that could be represented in the time domain as a signal Vm cosine omega t plus theta v. And the current flowing through this element will also be a sinusoidal signal that we could represent mathematically as Im cosine omega t plus some phase angle theta I. Now, in our analysis here, because we're looking for frequency domain relationships, the output of these relationships is going to wind up being a phasor. And so I'm going to start by looking at these signals effectively in the mixed domain. Right? So what I mean by that specifically is instead of using this cosine function, because to mathematically manipulate that is going to take trig identities and all of that kind of stuff, and I want to avoid that. Instead, I'm going to look at it as a exponential form complex number, Vm e to the j omega t plus some phase angle theta v. And I'm going to look at my current as an exponential form complex number, e to the j omega t plus theta I, where we have knowledge now that those time domain representations are really just the real part of those complex numbers. So we're dealing with the same information either way. So what is the relationship between voltage and current in a resistor? Not a trick question. Yeah, V is equal to IR, Ohm's law, just good old Ohm's law, nothing remotely fancy whatsoever, okay? So even in the time domain, it should still be just Ohm's law, okay? So what I'm going to do now is I'm just going to substitute in those complex number forms of V and I, right? So on the left-hand side, I have Vm e to the j omega t plus some phase angle theta v will be equal to, I'm going to move the r to the left-hand side here, r times Im e to the j omega t plus theta I. And now I'm going to split those exponentials up. Okay. So I could write Vm e to the j omega t plus theta v as e to the j omega t times e to the j theta v. And I can split up the exponential on the right-hand side of the equal sign as well, doing the exact same thing. And now we can very easily see that there is a common factor of e to the j omega t that's present on both sides of our equal sign. And so those guys effectively just cancel each other out. This is actually what lets us throw away the omega t part when we're dealing with phasors. Because everything is going to be oscillating at the exact same frequency, that's always redundant information, and we no longer really need to keep track of it. And this mathematically tells us exactly why. because it's everywhere, it's going to wind up canceling out on both sides of any equation that we have. So this leaves us with Vm e to the j theta v is equal to r times Im e to the j theta I. And to me, this looks like an exponential form complex number on the left-hand side of the equal sign and an exponential form complex number on the right-hand side of the equal sign. Why that's important is because if I have complex numbers on both sides of the equal sign and they're of the same form, then I can say that the magnitude of the left-hand side has to equal to the magnitude of the right-hand side. The phase angle of the left-hand side has to equal to the phase angle of the right-hand side. And that lets me glean some information about the behavior of resistors in the frequency domain. So looking at this, I can see that the magnitude on the left-hand side, which is just Vm, must be equal to the magnitude on the right-hand side, which is R times Im. So the magnitude of the voltage drop across the resistor will be equal to the resistor value times the magnitude of the current flowing through it. Effectively just obeying Ohm's law, nothing remotely fancy there. If we look at the phase angles, the phase angle on the left-hand side is theta v, and this has to be equal to the phase angle on the right-hand side, which is simply theta I, which means there is no phase change between the voltage and current in a resistor. Now, Vm e to the j theta v in exponential form could be written in polar form as Vm angle theta v. And over here on the right-hand side, we could write this guy as R times Im angle theta I. Well, what are those two things? Those are just our phasors, right? So on the left-hand side, we have our phasor voltage V will be equal to R times our phasor current I. And this is effectively just Ohm's law in the frequency domain. Right? So we have a relationship between current and voltage in the frequency domain that exactly matches what we saw in the time domain and DC circuits, all of that kind of good stuff. Ohm's law is always just going to be Ohm's law. That's one of the best things about it. So the frequency domain is kind of like the mathematical space where we are going to analyze AC circuits in order to avoid having to use a whole bunch of trig in calculus. Okay. So in the frequency domain, we're going to represent all of our voltages and currents as phasor quantities. So instead of a big time domain quantity like this, where we explicitly have cosine functions and all of that kind of good stuff, instead, we're going to represent it as a phasor where we're only keeping track of our magnitude and our phase angle for voltages and currents. In the frequency domain, we are going to represent inductors, capacitors, and resistors in terms of their impedance, which can be thought of as a frequency-dependent resistance. We haven't yet got to impedance, but we're going to cover that probably in the next 20 minutes. Yes. Yeah, so keeping all of that extra stuff in, so working explicitly in the time domain, means that all of our relationships are going to be governed by trig identities and calculus, which is definitely doable, but it is a gross, obscene amount of math, okay? By working in the frequency domain, all of those trig identities and calculus actually wind up just turning into simple algebraic relationships. And that's going to allow us to do the exact same circuit analysis that you learned in your previous classes and apply it towards AC circuits without having to really change anything other than the fact that now complex numbers are introduced. Right. Yeah, so chances are you never did any work in the time domain for your AC circuits at all, just because the math is so wildly difficult. If you want to see how gross it is, I've got videos on my YouTube channel of me working very, very simple problems in the time domain, and it literally takes 25 to 45 minutes for a simple 3-element network because the math just gets so wildly gross. So this is just setting up the foundation of why we work. Yeah. Yes.
So if you don't have the same frequency, you must work in time.
No. So
If this, so you need to.
the time domain is what, okay, so that's a very, very good question. What's the point of the time domain? That's what we actually deal with every day. The signal that's coming out of this outlet is a time domain signal. The frequency domain is just a mathematical construct to make the math easier so that we don't have to do it, because as it turns out, all of our work that we do in the frequency domain, we can bring back to the time domain without actually having to do any math in the time domain.
Okay.
So the time domain is the real thing. The frequency domain is a mathematical construct to avoid gross math. Yeah. All right, so let's look at an inductor. So here I have my inductor L. Once again, I'm going to have a voltage V of t across it and a current I of t flowing through it. And we're going to use those exact same voltages and currents from before. So I'm not going to bother writing them down again. It's literally the exact same ones we use, for our resistors. So can anybody tell me what the relationship between voltage and current for an inductor is supposed to be?
It should be the same as the resistor.
Very much not the case. Now, I'm not sure if you guys have covered this, so I might be springing something on you. But in the time domain, the voltage drop across an inductor is equal to the inductor value L times the derivative of the current with respect to time. Have you guys not even in your physics classes or anything like that?
That was a year ago.
Yeah, okay.
I'm assuming we looked at this. We definitely did not.
Okay.
Yeah, this isn't like calculus-based physics or anything like that. This is all like.
Oh, gross, 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 gross. Okay, well, you're just gonna have to take it on faith that this is how it works. Yeah, okay. So it's gonna be less obvious to you guys why the frequency domain is such a fantastic thing, but we'll get there. Okay, so we have a calculus-based relationship here, okay? Do you guys know how to take the derivative of a function? Okay. So,
like calculus in any other class.
okay, well, we're gonna do a little touch of calculus here, okay? So if I substitute in my complex number representation of my voltage, I'm gonna have Vm e to the j times omega t plus theta v here. And this is going to be equal to L times the derivative with respect to time of Im e to the j omega t plus theta I. So how do I take the derivative of that current, right? I'm taking the derivative with respect to time. So the Im part is a constant, so I'm not going to have to worry about that. The only thing I'm actually taking the derivative of then is that exponential function. So perhaps it's been a while for you guys, and that's okay. the derivative of e to the alpha t, where alpha is just a generic coefficient, is simply alpha e to the alpha t. Okay. So that means that this derivative is going to look like j omega, and then we're going to have the L, Im, and now we have the e to the j omega t bit again. So our derivative in the time domain is simply multiplication by j omega in the frequency domain. And that will always be true. So now I can do what I did earlier and split my exponential number up. So Vm e to the j omega t times e to the j theta v will be equal to j omega L Im e to the j omega t e to the j theta I. And I can see that my e to the j omega t terms go away on both sides yet again. So even for an inductor, it's okay for us to completely suppress our frequency. It's not going to matter at all. So we can just effectively throw it away. And what we're left with is Vm e to the j theta v is equal to j omega L times Im e to the j theta I. We have a very small problem here. At least when I'm trying to find the equivalence between the magnitudes and the equivalence between the phase angles. And that small problem is that on the left-hand side, I have a exponential form complex number. And on the right-hand side, I have a rectangular form complex number, j omega L, being multiplied by an exponential form complex number. So I need to figure out how to express j omega L as an exponential form complex numbers so that I can draw equivalency between the phase angles on each side. So I want to show you guys something really quickly here. So if this is my complex plane where this is real numbers and this is imaginary numbers, if I go out 1 unit in the positive real direction, which we would very commonly simply call the number 1, in rectangular form, this would be more formally expressed as 1 plus j0, right? There's 1 in the real part, 0 in the imaginary. Okay? In exponential form, this would look like 1e to the j, 0 degrees. And in polar form, this would be 1 angle, 0 degrees, because it's forming an angle of 0 degrees with the positive real axis, right? So we can do something similar if we go out 1 unit in the imaginary direction. We would normally call this j. More formally, it would be 0 plus j1. What do you think it's going to be as an exponential number? So 1 e to the j, what's the angle formed with the positive real axis? I disagree. What's this angle? 90 degrees. And then in polar form, this would be 1 angle, 90 degrees. We could keep on going. So over here, we would have -1 or -1 plus j0 or 1, e to the plus or minus j 180 degrees or 1 angle plus or minus 180 degrees. And it's plus or minus because it doesn't matter if we go over the top or around the bottom, it's still 180 degrees either way. And then if we go -1 unit in the imaginary direction, that would be negative j, or 0 minus j1, which we could write as 1e to the negative j 90 degrees, or 1 angle negative 90 degrees. So effectively, we could replace this j right here with 1e the j 90 degrees. They're literally the exact same thing. That's just the exponential form representation of j as a rectangular complex number. So what's going to happen when I multiply e to the j 90 degrees times e to the j theta I? The theta I and the 90 are going to add together. So this is going to look like omega L Im e to the j theta I plus 90 degrees, right? So when I multiply two exponentials together, the arguments of those exponentials add. Doing that backwards is exactly how we were able to split up our exponentials earlier. Okay? So now I have it in a form where I can explicitly see a magnitude on both sides and a phase angle on both sides, so I can see how those things relate to each other. Right? So from this representation right here, I could say that the magnitude of my voltage, Vm, is going to be equal to omega L times Im. And I can also see that theta V is going to be equal to theta I plus 90 degrees. So that means that the phase angle of the voltage is always 90 degrees more positive than the phase angle of the current. Okay? So we're always going to see a 90-degree phase shift between voltage and current in an inductor. When we start talking about power relationships, we're going to call that the voltage is leading the current by 90 degrees. Or another way to think about it would be the current is lagging the voltage by 90 degrees. And it's just saying there's a phase shift of 90 degrees between them, and which one is hitting its peak value earlier in time is all that means.
The first has to be really except for our last binding term where we would have negative 90 as a positive.
Absolutely. We'll do that just in just a moment. So looking at these guys right here as well, so Vm e to the j theta V we know is simply our phasor voltage. And then we could have j omega L times Im angle theta I, and we could express this as V is equal to j omega L times I phasor. So seems like you're probably familiar with these end results here, and we're just kind of showing you why they exist. All right, so now let's talk about capacitors. And we're going to do this one pretty quickly because it's so incredibly similar to how inductors work, except that I and V are going to be switched, and everywhere that we used to have L, we're going to have C. So here's our capacitor. Here's our voltage drop. Here's our current. Our time domain relationship is the current across a capacitor is equal to the capacitance times the derivative of the voltage. Looks incredibly similar to what we just saw for an inductor. And so what we're going to wind up having is Im e to the j omega t plus theta I is equal to C times the derivative with respect to time of Vm e to the j omega t plus theta V. We're going to skip a couple of steps here because we already figured out how all of this math works when we looked at the inductor. We're just changing voltage and current here effectively. So what we're going to wind up having over here on the left-hand side is Im e to the j theta I. And on the right-hand side, we could have j omega c times Vm e to the j theta V, or using our identity for what j is, this could look like omega c times Vm e to the j theta V plus 90 degrees. This representation allows us to see that the magnitude of the current is equal to omega c times the magnitude of the voltage, and theta I is equal to theta V plus 90 degrees, or what's your name again, Trilon? What Trilon suggested a moment ago is if we moved theta V to the other side of the equal sign or put it by itself, we would have theta I minus 90 degrees, which is exactly what he suggested, right? So for a capacitor, we can see that we once again have a 90-degree phase shift between current and voltage. However, this time, the phase angle of the current is always 90 degrees more positive than the phase angle of the voltage, which means the current leads the voltage in a capacitor. And so anytime we deal with capacitance, we're going to wind up having leading power factors. And we'll talk about that more, I think, next Tuesday. All right, so looking at this representation, we can see that this is simply Im angle theta I expressed as a polar form complex number is equal to j omega c times Vm angle theta V. And expressing it in terms of phasors explicitly, we have I is equal to j omega c times V phasor. So these are our relationships or how expressions for how voltage and current is related to each other in resistors, capacitors, and inductors in the frequency domain. So now let's talk very briefly about the concept of impedance. So let's take a step back to Ohm's law effectively in a DC circuit. So Ohm's law was experimentally determined by this German physicist named George Simon Ohm. And so what he found is that if he took any two terminal network, so I'm just going to call this a black box network, doesn't particularly matter what's inside, and he excited this network either by applying a voltage or a current to the terminals of the network. When he measured the voltage drop across the terminals and the current flowing into the network, he found that these two quantities were always proportional to each other, and that the ratio of V divided by I is what he called the resistance of the material. We can do something very similar in an AC network. Okay? So if I take a generic AC network, doesn't particularly matter what's inside of it. And I sinusoidally excite it. If I can measure the phasor voltage across the terminals of the network and the phasor current flowing into the terminals of the network, then the ratio of the phasor voltage to the phasor current will effectively be what the AC resistance is. We call that AC resistance impedance Z. So our impedance Z, by definition, will always just be the ratio of the voltage drop across whatever it is we're interested in, divided by the amount of current flowing into whatever it is that we're interested in. Now, since impedance is a ratio of two complex numbers, impedance must also be a complex number, right? So that means that we can express it in both polar form and rectangular form. So let's see what that entails really quickly here, right? So this would be Vm angle theta V divided by Im angle theta I. So this is just division of two polar form complex numbers. We know how to do this after our last class meeting. So this is just going to look like the ratio of Vm divided by Im with an angle of theta V minus theta I, or the magnitude of our impedance angle, the angle of our impedance, right? So the magnitude of our impedance is always just going to be the ratio of the magnitude of the voltage over the magnitude of the current. The phase angle of our impedance is always going to be theta V minus theta I. So there's our rectangular form representation, excuse me, our polar form representation. The rectangular form representation is a little bit more interesting to me, right? So in rectangular form, we're going to have the magnitude of Z cosine theta Z plus J times the magnitude of Z sine theta Z. That's just using our identities that we developed in our last class to convert that polar form number into a rectangular form number. We typically call this guy right here, the real part, resistance. And the imaginary part of this guy right here, X, is what's called reactance. Okay? So that our impedance could be expressed as simply R plus JX. So now let's use the definition of impedance to figure out what the impedance of a resistor, a capacitor, and an inductor is going to look like. So for a resistor, we know that phasor voltage V is equal to R times phasor current I. We literally just figured that out a few moments ago. So from this, the impedance of a resistor is literally just the resistor value itself. Expressed more formally in rectangular form, this would look like R plus J0. And in polar form, this would look like R angle 0 degrees. Now, what are the units of resistance? Ohms, absolutely right. For an inductor, we know that V is equal to J omega L times I. So the impedance of an inductor is simply J omega L. Now, it's shown here explicitly by math that the impedance of this inductor is frequency dependent because there is some value of omega here, but let's talk very briefly about what that exactly means, right? So let's say that we were operating at very, very low frequencies, like, I don't know, DC, right? Where omega is equal to 0. What would the impedance of an inductor look like in a DC circuit? 0 ohms, or 0 units, which we're going to find out are ohms in a minute. Does this agree with what you guys have learned previously, that inductors behave like short circuits in DC circuits? Yeah, it's right here. This is where that comes from. Okay. Omega is indeed angular frequency. So just to come back up here to what we were talking about earlier, the omega in our impedance relationship is literally the omega that our voltage and currents are oscillating at. The angular frequency of our voltage and current signals tells us what our impedance is going to be. And those impedances are going to change if the frequency of our network changes, right? So just a moment ago, we found that at very, very low frequencies, an inductor looked like a short circuit, because when omega is very, very small, omega times L is going to be a very small number close to 0. What do you think is going to happen if omega is really, really high? What? It'll trend towards looking like an open circuit. Absolutely, right? So at very, very high frequencies, depending on what the value of L is, changes what high frequency means, but the inductor is going to look more and more like an open circuit as we hit higher frequencies. Okay. What was your question? We'll talk about that in just a second. So that's a very, very good question, though. Okay. Omega is represented in radians per second, but it is related to linear frequency in hertz, and we'll talk about that.
So we get any farther than the people or like pulling false connection. I just need you to differentiate reactance and resistance because they combine into a single term. So I always call them reactance as being like resistance too. But I know
but it's imaginary resistance. Okay. So the reactance is the imaginary part of the impedance, and the resistance is the real part of the impedance. And so let's look at the resistance here really quickly, right? We can see very easily, if we're looking at the rectangular form, R plus J0, that a resistor only contributes to the real part of an impedance because it doesn't have any inherent reactance whatsoever. Now let's look at this inductance right here, expressed explicitly as a rectangular form complex number. It would be 0 plus j omega L in rectangular form, or omega L angle 90 degrees expressed in polar form, right? So we can see here that an inductor only contributes reactance. If we have a network that contains both resistance and inductance, then it'll have both real and imaginary parts. So let's look at the units here really quickly, okay? So we have omega, which is expressed in radians per second, where a radian is a dimensionless quantity. It's just form of an angle, right? And then we have inductance, L. So what are the units of inductance? Henry. What is the base units of a Henry? Volt second per ampere. So since radians are a dimensionless quantity, they're not going to contribute anything. We have a seconds in the numerator and a second in the denominator, so those guys are going to cancel each other out. So we're left with units of volts per amp. What's another way to call volts per amp? Resistance, or ohms. So the units of the impedance of an inductor is also expressed in ohms. which turns out will be a good thing for us here in a moment. Now let's look at a capacitor. So in a capacitor, we know that the current is equal to J omega C times the voltage. So the impedance of our capacitor is going to look like 1 over J omega C. Expressed explicitly as a rectangular form complex number, this is actually going to look like 0 minus J times 1 over omega C, or 1 over omega C with an angle of negative 90 degrees. Now, some of you may be wondering where the hell that negative sign came from, and that's a very reasonable thing to wonder. So let's talk about that really quickly, okay? So let me do this in blue. If I have 1 over J, and I multiply that by J over J, what I'm left with is J divided by J squared. Well, what's J squared again? Negative 1. So 1 over J is the exact same thing as negative J. So that's why I was able to just pull that 1 over J from that first term and write it as negative J in the second term. I wrote it that way explicitly so that we could see that a capacitor is always going to contribute negative reactance to a network, okay? So an inductor will always contribute positive reactance. A capacitor will always contribute negative reactance. That is always true. It will never not happen that way. That's the number 1. J over J. I put it there explicitly so I could explain how I got from 1 over J to negative J, but J over J is just me multiplying by a special form of the number 1 to show you how I got that result. Yeah. So if I have 1 over J, I multiply by J over J, that gives me J over J squared, where J squared is negative 1. And so J over negative 1 is the same thing as just negative J. For our units, now we're going to have 1 over omega. So that's going to look like seconds per radian. And then we're also going to have 1 over our capacitance, where capacitance is measured in farads. And a farad has base units of amp seconds per volt. So amp seconds per volt. And once again, the radians don't contribute anything because it's a dimensionless quantity. We have seconds in the numerator, seconds in the denominator, so those guys cancel each other out. We're left with just volts per amperes, which, as we have already determined, simply ohms. So the impedance of a capacitor is also measured in ohms. Okay, so let's answer, what's his name? Brock. Let's answer Brock's question about stuff measured in hertz, okay? So this angular frequency is always quantified in radians per second. But typically in a physical system, like here in the United States, we say that we operate at a frequency of 60 hertz. In most regions of Europe, it's 50 hertz. Other places, it might be slightly different things, right? So let's talk about the relationship between linear frequency F, which is measured in hertz, and angular frequency omega, which is measured in radians per second, okay? This is a quick tangent, but it is very necessary. So F, linear frequency, which is measured in hertz, is the number of cycles per second in a system. Angular frequency, omega, measured in radians per second, is the change in angle per second in our system. Now, let me ask you guys a question. How much of a change in angle occurs? Our, what's it called, projector reset itself again. Apparently that's going to happen every damn class meeting for whatever reason, but we can talk about stuff. What is the total change in angle that is experienced in a single cycle for a sinusoidal signal? 360 degrees, or 2 pi radians, right? So let this. Okay. So if I have omega is the change in angle per second, that's simply going to be 2 pi times my linear frequency, because you could interpret that as there is 2 pi radians per cycle multiplied by the number of cycles per second gives us radians per second as a unit. So that's the relationship between linear frequency and angular frequency. So let's talk about that really quickly. Fantastic question. Okay. So as another thing here, our period, which is measured in seconds, typically. This is the time it takes for one cycle complete, right? So our period is literally just the inverse of our linear frequency, because if frequency is the number of cycles per second, period is the number of seconds per cycle, okay? So that means that our angular frequency omega is simply 2 pi divided by our period. So if we ever had a sinusoidal signal and we were not sure of what its angular frequency is, but we could figure out what its period is, this gives us a relationship to find our angular frequency omega. So from these relationships, you should be able to figure out the impedance of any sinusoidal network, regardless of whether or not I tell you what the period is, what the angular frequency is, or what the linear frequency is, because you know how to get to omega from any of these quantities. Which if you look at homework set number 1, problem 3, I think in the first problem, I asked you to find the impedance, equivalent impedance seen between the pair of terminals with an angular frequency. And in the second problem, I asked you to find the equivalent impedance seen between a set of terminals using the linear frequency. Just as a quick exercise, let's look at maybe that in-class assignment problem 3 from the last class meeting. Okay, let's see. Sorry. so many classes. All right, so here is our problem statement and all of that kind of good stuff. We have a network, and we are asked to find the equivalent impedance seen between the terminals A and B for an operating frequency of F is equal to 1 kilohertz. So if F is equal to 1 kilohertz, what would omega be? We just multiply F by 2 pi. So if F is 1,000, then we would have 2,000 pi as our angular frequency. So nothing particularly wild or crazy there. So what is the impedance of that 25 ohm resistor? 25 ohms. The impedance of a resistance literally does not change. So this resistor, and this resistor, we don't touch. What about our capacitor, right? So the impedance of our capacitor, ZC, is going to be 1 over J omega C. We know the units are going to work out to give us ohms, so I'm just going to drop the units here because we've already explained what's going on there. So that's going to be, actually, let's write it like this. Negative J times 1 divided by 2,000 pi. And then we have 10 millifarads, so that's going to be 10 times 10 to the minus 3. If we put this in our calculator, one over 2,000 pi times 10 times 10 to the minus 3. I get negative J times 0.1016 ohms of impedance from this capacitor. Okay. That is rounded a little bit, so our final answer might not be exactly the same as what we're going to get because of rounding error, but it'll be okay. So we would treat this guy as a negative J 0.016 ohm capacitance or impedance. For our inductance, we're going to have J omega L. That's going to look like positive J times 2,000 pi times 20 times 10 to the minus 3. That comes out to be 40 pi or positive J 125.664 ohms. So we can scratch that out and put J 125.664. So now that we have expressed everything in terms of impedance, this effectively just became a resistor combination problem, right? So how would I find the equivalent impedance of this? So, okay, so the 55 ohms in parallel with the J 125.664 ohms, absolutely. That would be in series with the capacitance and the 20 ohm resistance, lump all that together, put it in parallel with the 25 ohm resistor, done. So once we get into impedances, like I said, it just becomes a simple resistor combination problem that you guys should be pretty comfortable with. Okay. So this is what the process is going to look like. All right. So let's go back over here to our notes. Oops, wrong tab thingy. Okay, so we know how voltages and currents are going to behave because we know that we're just going to represent them as phasors. We now have figured out how to represent all of our resistors, capacitors, and inductors as impedances. So let's put these two concepts together and talk about circuit analysis in the frequency domain. Okay. So today, we're going to work, I'm going to say easy, and I'm going to probably seem like a jackass for saying that in a moment, but I'm going to say easy problems. And what I mean by easy problems is the ones that we can solve just using our calculator, just to kind of learn the ropes of things. On Thursday's class meeting, we're going to work harder problems that are going to require us to use a computer to solve our systems of equations because they involve complex numbers. So I believe I already put a link for you guys to download MathCAD and all of that kind of stuff on Canvas. Before class on Thursday, please have MathCAD downloaded and installed so that we can do some circuit analysis, and then I can show you guys how to use MathCAD to solve these complex systems. For what we're going to do today, and because it's already 9 o'clock, let's work one of these in-class assignment problems together. And then the second one I'll leave for you guys to tackle if there's enough time. All right. So let's look at problem 1 here. Okay. So this is the circuit that we are going to be analyzing. We have a 50 ohm resistor over here, 20 millifarad capacitor over here, an 80 millihenry inductance over here. Here's our sinusoidal current source, Is of t. Here's a 24 ohm resistor. Sorry, that should be an inductance, 30 millihenries. And I am asking you guys to solve for the following quantities. Ix of t and Vy of t. So I want to state something here. Because I'm looking for a time domain current and a time domain voltage, my expected answers are going to be some magnitude cosine omega t plus some phase up. even though I'm expecting to get a result of that form, we are going to do literally none of our work in the time domain because, like I said earlier, it's really gross. That's what the frequency domain is for. So the first thing that we're going to need to do here is to convert our circuit from the time domain into the frequency domain. Okay. Just as a quick thing here, our time domain source current is given by 18 cosine 35t plus 75 degrees amps. And so the first thing that I want us to do is to redraw the circuit, and then we're just going to convert all of our voltages and currents into phasor representations, and then all of our resistors, capacitors, and inductors into their equivalent impedances. Okay. So I'm just going to leave all of these element values blank. We'll get to them in a moment.
When we took the class, I found that the pieces to have both in one state, I would have an interchangeable folder. Is there, can I ignore one of the other?
Generally speaking, I deal with voltages and currents in polar form exclusively. Impedances, it kind of whatever feels appropriate. So you might see me do some in rectangular form, sometimes in polar form, sometimes mixed. Here, we're going to wind up probably doing everything in rectangular form with regards to our impedance. But that's the great part of these calculators that I've suggested you guys to buy is it doesn't care if you put it in a rectangular or polar or some combination thereof, it can just do the math. All right, so let's start with the phasor representation of our source current. So how am I going to convert that 18 cosine 35t plus 75 degrees amperes into a phasor current? 18 angle 75, absolutely right. We keep the magnitude, we keep the phase angle, we throw the rest away because it's already expressed in a cosine form. 100% correct. So 18 angle 75 degrees amps. Okay. Just for the sake of argument, I'm going to go ahead and express my current IX as a phasor. So that's just going to be this phasor current here, IX. And my voltage VY as a phasor is just going to be this voltage here. So now all of our currents and voltages that we could possibly be interested in or have information about are expressed as phasors. Now we should express all of our resistors, capacitors, and inductances as their equivalent impedances. So, oops, I put the 24 ohms up here, kind of giving it away, but the resistors are not going to change at all. So the 50 ohm resistor is going to look like a 50 ohm resistor. The 24 ohm resistor is going to look like a 24 ohm resistor. Nothing remotely new there. Okay. For our capacitor, we know that the impedance of a capacitor is 1 over j omega c. So that's going to look like negative j divided by, so what's omega here? 35, yep, so 35 radians per second. We'll just call it 35. Our capacitance is 20 millifarads. So 20 times 10 to the minus 3. And so let's see what that shakes out to be. So minus j 10 over 7 ohms is what I got. Anybody else get that? Now let's work on this 80 millihenry inductor. So that's J omega L. So it's going to be J times 35 times 80 times 10 to the minus 3. And that came out for me as 14 over 5. And we'll go ahead and do it for that second inductor. So that's going to be J times 35 times 30 times 10 to the minus 3. And that looks to me like 21 over 20. So we have successfully converted our circuit from the time domain into the frequency domain. After we get comfortable with this, I'm probably just going to give you guys circuits that are explicitly in the frequency domain to begin with, so that you don't have to do all of these converting your impedances over and all of that kind of good stuff. But for now, let's just take this as an opportunity to practice these relationships because they're important and we're going to be using them for a couple of classes and all of that kind of good stuff. Okay, so now that we have our circuit fully converted into the frequency domain, we can just apply effectively just regular good old DC circuit analysis techniques in order to solve for our quantities of interest here. Now, I know fully that we could tackle this problem using nodal analysis or mesh analysis, but for this particular problem, it is not necessary. So let's think about ways that we could get these different quantities without using nodal or mesh, because the calculators that we are restricted to literally cannot solve a system of equations that have complex numbers in it. So a problem like this would be very representative of something I might put on a test. This level of difficulty, number of components, all that kind of stuff. So anybody have any thoughts on how we might solve something like this that doesn't use nodal or mesh analysis? So when you say find the equivalent impedance, what do you mean by that specifically? Because I could see how that could be useful, and I can also see how it would be completely pointless depending on what impedance you're talking about.
On the right side. Getting that together.
So let's explore that really quickly. I'm going to take it one step further. I'm going to redraw this again. So I'm putting a box right here because this is how I choose to represent a generic element. And so what I'm going to do here is I'm going to lump together that resistor and that capacitor into a single impedance. So instead of being 50 in series with minus J10 over 7, I'm just going to call it all 50 minus J10 over 7 as a single thing. I'm going to do the exact same thing for the impedance on the right as well. So this would look like 24 plus J 21 over 20. I'm going to put a line here because I'm running into things. And now I'm going to label those quantities that I want. So IX and VY like so. It would not be annoying. However, I don't think it's necessary. Let me explain what I mean by that. So drawing it in this form, to some extent due to Nick's suggestion here, has shown me that I have a current source that is in parallel with 3 impedances. Okay. So that voltage VY is just the voltage drop across all of these things in parallel, which means realistically, I could find VY just by applying Ohm's law to this circuit. That current IS times those 3 impedances in parallel must give me that voltage VY. So that is definitely useful. Another way that I could interpret this particular circuit is that I have a current source in parallel with 3 impedances, which means I should probably be able to use current division to find the current through any one of those branches, like the one on the right that I'm asked for. Are you guys familiar with current division? You feel like you have or have not? Ron, have they or have they not? We touched on it. Oh. Okay, well, let's do some more with it here because it can be a very, very powerful tool. Okay, so I'm going to do this without deriving the relationship. If you want to see how it's derived, which you probably don't, but somebody might, it's in my circuit analysis lectures and all that kind of crap on YouTube. But how current division works in general is something like this. The current that we want to find, so I'm just going to call that in this case IX because that's literally what we're looking for, is simply going to be a known current multiplied by a ratio of resistors, or in this case, impedances, right? So this would be 1 over, I'm going to call it ZX in top or on top. So the impedance in the numerator is the one we're trying to find the current through. And then on bottom, it's just going to be the sum of the reciprocals of all of the impedances that are connected in pairs. So applying this relationship to our specific circuit is going to look something like this. IX will be 18 angle 75 degrees amps times. So the impedance that we're trying to find the current through is the 24 plus J 21 over 20. So I'm going to put 1 over 24 plus J 21 over 20 ohms here. And then now I'm going to put all 3 of those parallel impedances in my denominator, right? So that would be 1 over 50 minus J 10 over 7 plus 1 over J 14 over 5. Sorry, that looks too much like a minus J there. Let me fix that. Plus 1 over 24 plus J 21 over 20. And now I can just put this whole thing into my calculator. chances are if you have a Casio calculator, you're going to want to put this in multiple steps because it seems to run out of memory faster than the TIs. So how many of you guys are familiar with storing numbers in your calculator? So that can make things way, way easier for this stuff, okay? So what I'm going to do is I'm going to store stuff in my calculator to just make my life significantly easier. So I'm going to put 24 plus 21 over 20. Actually, let me change this to the right mode. There we go. So 24 plus 21 over 20i. And I'm going to store this in my calculator as A. I'm just going to make a quick note here that this is stored in my calculator as A. Then I'm going to do 50 minus 10/7 I, store that in my calculator as B. And 14 over 5I, store that in my calculator as C. If anybody needs help storing numbers in their calculators, let me know. So what that's going to do is allow me to express this with way less overall typing and all of that kind of stuff, and I'm way less likely to make a mistake. So now I can put in 18 angle 75 times 1 over A divided by 1 over A plus 1 over, 1 over B plus 1 over C. And I get, thinking, 2.060 with an angle of 152.747 degrees amps, which I'll be damned is exactly the correct answer that I provided you guys on the sheet, right? This is doing this using current division. Okay. To find Vy, we could just use Ohm's law. So that would be 18 angle 75 degrees amps times 1 over 50 minus J 10 over 7 plus 1 over J 14 over 5 plus 1 over 24 plus J 21 over 20, right? So just to be clear, all that is the current multiplied by those three impedances connected in parallel. In my calculator, that's going to look like 18 angle 75, 1 over A plus 1 over B plus 1 over C, close parentheses. And we get, sorry, it's zooming, 49.499 with an angle of 155.252 degrees. So technically speaking, we are not quite done. The reason why I say that we're not quite done is because we got phasor voltage and phasor current, but I want time domain voltage and time domain current. So how do I convert these signals back from the frequency domain into the time domain? So Ix, I'm going to take my magnitude, 2.060. I'm going to have cosine. What was omega again? 35. So I'm going to have 35t, and then now I put the angle back in. And Vy of t, I'm going to do the exact same thing. So somebody tell me what that's going to look like. Yep, 252. There we go. We've analyzed the circuit in the frequency domain. That's just one possible way to analyze the circuit. Sure. No, I don't have any problem with it. I just want to show you guys something else here really quickly, but also I want to figure out why my computer isn't charging. Give me just a second. Okay, maybe that out just it. So I'll answer your question, or I'll show you voltage division in just a second, but I want to show you guys a different way that we could have solved this that might wind up being a little bit easier. This will not work for all circuits by any stretch of the imagination, but it will work for circuits like this where we only have really one unknown voltage. So I'm going to take this representation right here. And we're going to reanalyze this circuit. And what we're going to do is, I'm going to call it modified nodal analysis, but realistically, it's just Kirchhoff's current. So when I have a circuit like this, where there's really only one unknown voltage, and this one's going to be incredibly simple because we can see that everything is directly connected in parallel, I could choose one of my nodes as ground, and I could put a nodal voltage at my unknown thing. And so now I can just write a KCL expression here. So I would have Vy divided by 50 minus J 10 over 7 ohms plus Vy divided by J 14/5 of an ohm minus 18 angle 75 degrees amps plus Vy divided by 24 plus J 21 over 20 ohms is equal to 0. And now I can do a very quick amount of algebra here. So I could say that on the left-hand side, I have Vy times 1 over 50 minus J 10/7 plus 1 over J 14/5 plus 1 over J, excuse me, 1 over 24 plus J 21 over 20 is equal to 18 angle 75 degrees amps. And now if I divide both sides by that big expression that's multiplied by Vy, that allows me to solve for Vy. In this case, that's literally the exact same thing as doing Ohm's law, but in other circuits, it won't be, but that method will still work. If we can draw our circuit in such a way that there's only one unknown voltage. So for instance, in the second problem of the in-class assignment, we look at that really quickly. If you were to lump these two elements together as a single equivalent impedance, actually, you know what? We're going to work this one too, because I can use voltage division for this one. So let's work this second problem here. So we're going to do this pretty quickly because we've only got 20 minutes. This voltage source is going to look like 15 angle 30 degrees volts. Everybody okay with that? Okay. My inductance is going to look like 215 times 10 to the minus 3 times 10. So this guy right here is going to look like J 43 over 20 ohms. This guy over here is going to look like 1 over 10. I do it as fractions just because you get less rounding error. Yeah. 88 times 10 to the minus 3. And so this is going to be negative J 25 over 22 ohms. Right? Just for the sake of argument, this is now going to be a phasor voltage Vx. This is now going to be a phasor current Iy. So I could employ that technique that I just talked about to this particular problem by saying that, let's call it this voltage right here. Let's call it Vz for the sake of argument, is my only unknown voltage. And this guy right here is going to be my ground. So to me, my KCL equation for this guy would look like Vz divided by 8 plus J 43 over 20. That's just the current flowing to the left through these two elements in series. Plus Vz minus 15 angle 30 degrees volts divided by 3 ohms. That's just this current flowing down through the 3 ohm resistor. And then now I'm going to do this current over here. So Vz divided by minus J 25 over 22 ohms is equal to 0. Anybody have any questions about that Kirchhoff's current law equation there? So now I can just rearrange things. So that's going to look like Vz divided by, excuse me, multiplied by 1 over 8 plus J 43 over 20 plus 1 over 3 plus 1 over minus J 25 over 22 is equal to 15 angle 30 divided by 3 ohms. And so I'm going to put this big thing in my calculator and save it as A. And I'm going to put this thing in my calculator and now save it as B. So 1 over 8 plus 43 over 20 I plus 1 over 3 plus 1 over negative 25 over 22 I, close parentheses, store it as A. This came out to be 0.961, angle 62.070. If I didn't make any mistakes. 15 angle 30 divided by 3 should just be 5 angle 30. Store that as B. And now VZ is just going to come out to be what I have stored in my calculator as B divided by what I have stored in my calculator as A. Or 5.205 angle negative 32.070. And I'm going to store this as C. So let me scroll back up here. The voltage that I just solved for literally isn't a quantity that I was explicitly asked for. However, I can use it to get the quantities that I'm interested in extremely easily, okay? So let's look at that current IY first because it's the easier one. So the voltage VZ is the potential difference between this node and this node. So that voltage VZ is literally the voltage drop across that negative J 25 over 22 ohm impedance, which means IY should just be VZ over negative J 25 over 22 ohms. Or 4.581 with an angle of 57.930 degrees. Which seems to match exactly what we would expect given the answer, right? Now let's talk about how we can use that voltage VZ to find the voltage VX, and we're going to use voltage division in order to do that, right? So our generic equation for voltage division is going to be Vx is equal to some known voltage times the ratio of Zx over Z1 plus Z2 all the way out to Z sub X, where Zx is the impedance of interest. Applying this to our relationship, we'll have Vx is equal to Vz times, so the impedance that we're trying to find the voltage drop over is the J43 over 20. And then our impedances in series is just the 8 and the J43 over 20. So putting this into my calculator, I wind up getting 1.351 with an angle of 42.887 degrees volts, which once again agrees with what my expected answer should be. So this methodology will not always be there because it relies on effectively us being able to set up a one equation, one unknown system in order for us to solve. But in simple circuits like this, where I can't expect you to have to use a calculator or anything like that, it's definitely a good trick to have in your back pocket. And you could do things like source transformations, impedance combinations, and all of that kind of stuff to reorganize your circuit in a way that you can apply this trick in a lot of instances. But anyway, all right. So we worked actually both in class assignment problems. So I guess we're done for today. I can hang around for another 10, 15 minutes if anybody has any questions about anything or how to use the calculators and all of that kind of good stuff. And just to remind you, please install MathCAD and all that jazz before our next class so that we can tinker with it.